I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we will briefly discuss about iterative deepening A star search, that is IDA search. Iterative deepening A star is a search algorithm that combines the benefits of both iterative deepening depth first search IDDFS and the A star algorithm. IDA star seeks to find the optimal path from the start node to the goal node in a weighted graph by incrementally deepening the search based on the threshold value determined by the F score, which is the sum of the actual cost from the start node G of n and the estimated cost of the goal node H of n. Unlike the traditional A star, IDA stars operates with minimal memory usage. That is the main advantage of using IDA star. Minimal memory usage by discarding nodes as it moves deeper into the search tree, making it particularly useful for solving large scale problems with limited memory resources while still guaranteeing optimal solutions. So next we will see one by one why this iterative deepening A star search is called as a memory efficient algorithm. This IDA star is a memory efficient pathfinding algorithm that combines so it combines two things here. DFS, all you know that what is DFS? DFS means depth first search. It combines the DFS and heuristic function and combines the heuristic function. It reduces the memory usage by exploring one path at a time and discarding nodes as it deepens the search. IDA star incrementally increases the search threshold based on the F score, that is sum of the actual cost and estimated cost, and prunes the path that exceed this threshold. This will see it in the problem that minimizes the memory requirement while still ensuring the discovery of the optimal solution. This makes IDA star particularly useful for solving large scale problems where memory efficiency is a priority. Next one is this IDA is an efficient graph, how means traversal and pathfinding algorithm designed to find the shortest path in a weighted graph. Okay, it combines the depth first search with the heuristic estimate to guide the search. That is, IDA star uses incrementally increasing the threshold based on the F score and which balances the memory efficiency and optimality. This makes it well suited for large scale problems where memory is limited. This IDA star combines the IDDFS, that is iterative deepening depth first IDDFS and A star search to efficiently find the shortest path. Efficiently find out the shortest path. It uses the heuristic function to estimate the remaining cost to the goal node. The algorithm iteratively deepens the search while adjusting the threshold based on the F score. This ensures both memory efficiency and optimal pathfinding. Next, IDA star is a memory efficient. What I've said, IDA is often called the memory efficient because it uses the depth first search and only stores the current path. It stores the current path search and rather than the entire search tree. It reduces the memory usage by discarding the nodes as search progresses. Despite its lower memory requirement, IDA store still guarantees the optimal pathfinding. This make it ideal for problem with the large state spaces where memory is limiting factor. Next, so how this IDA star works? IDA star incrementally increases the threshold based on the F score. This F score is calculated by using f of n is equal to g of n plus h of n. You know that f of n is the total cost, g of n is the actual cost from the start node to the current node, h of n is the heuristic estimated cost from the current node to the goal. And this h of n must be the admissible, meaning it should never overestimate the actual cost to the goal. The heuristic is problem specific and plays a crucial role in finding the search efficiently. Next, what is F score? F score is a heuristic function used to estimate the cost of reaching the goal state. So it combines two heuristics, what I have said, G of n and H of n, and F of n is equal to G of n and this F of n is equal to G of n plus H of n. It determines the order of the node expansion in the search tree and So here, what we can, this score determines the order in which the nodes are expanded in the search tree, which nodes having the lower F score here, lower F score being closer to the goal, and therefore expanded first. This helps the algorithm prioritize the most promising path. This step all you should remember. Next, what are all the procedures used, step-by-step procedures used in IDA? It begins with the initialization by defining the root node as the initial state computing its F score. If the threshold is setup steps and the initial threshold is established using the F score in this case. And the next child node are generated and their respective F scores are evaluated during the node expansion phase. Nodes that exceed the threshold are discarded through the pruning strategy while they are stored for later consideration. If the goal node is reached, the path identification stop reconstructs the path from the start node, the goal node. If no solution is found, what will happen? No solution is the algorithm increases the threshold based on the smallest pruned values and repeats the process during the threshold adjustment. So these six steps are being used for finding the IDA star or in the shortest path. So in this iteration, so this is the example problem which I have taken for explaining this IDA star algorithm. Okay, here what is happening, this is the uh, this example demonstrates the how IDA star efficiently explores the state space while the maintaining the memory. So the first case in this iteration, the IDA star algorithm, the root node. This node is the root node, and what is the value? 2 was given as set as the current node. This node is the current node. Correct. Which is the value is 2. The algorithm then explores the child nodes of root node, the first child here. So the threshold we are setting up to the first child has here, this is the first child, value is 4, here 5. 4 is greater than 2 and 5 is also greater than 2. So in this step these two are pruned. So the visitor values are 4 and 5, these two are pruned. So it is pruned, not expanded further. Similarly, the second child 5 also exceeds the threshold 5, so it is also pruned. As a result, the iteration ends with the pruned values 4 and 5. The 4 and 5, meaning these nodes will not be explored in this case. Okay, coming into the next iteration, among these two pruned values, we have to consider the lowest value between these two, which is the lowest value 4. So in the next iteration, so this is the step all you have to follow. Just tell you half minute pass, root node, current node, and the threshold is pruned, and 5 is greater than threshold. Threshold value is what? First step 2. So iteration complete, the pruned values are 5. For the next step, we are considering 4 as the threshold value. So we are going to expand over here, and which is the least pruned value from the previous iteration. Correct. This algorithm begins with the current node. Begins with the current node here 4, which is less than the threshold, less than the threshold. So it is accepted. It proceed to explore its children. The first child of 4 is set to as no. First child is 4, and the next one is the 5. The child 5 exceeds the threshold. 5 is greater than 4, so it is pruned here. And so the second child of node 4 is explored because 4 is equal to 4 threshold value. Correct. The children are 8 and 7. 8 is greater than 4 and 7 is also greater than 4. These two are pruned in this iteration. Correct. So they are pruned. Next, the second child of root node 5 is explored but pruned as it exceeds the values. Exceeds the value 4, as at this iteration the pruned values are 5, 8 and 7. 5, 8, 5 and 8 and 7. So among these 5 and 8, 5, 8, 7, going into the next iteration, 5 we have to select as the current node. So so only can follow this step. I'll give you half minute pass. So whatever I have explained by using this, I have given it in this case. So next iteration threshold we are setting it as 5 because in this case we are, what are all the nodes we have taken? 5, 8, 7 is a prune node. So 5 we are considering. The updated threshold is set to 5 here. which is the least pruned value from the previous step. The root node, here the root node is 2, the current node is the current node, and since the value is 2 less than the threshold, 2 is less than 5. The algorithm proceeds to explore its children. The first children is 4 and has a value 4 which is also less than the threshold. So the algorithm sets to node. So here the 4 is less than that is 5 less than 5 which is also less than the threshold. So the algorithm sets to node 4 as the current node and explores its children. The first child of the node 4 is 5. Here node is 5. The second child is 4 which is equal to the threshold. This 5 is equal to 5 and 4 is less than 5. So these two can be expanded, 7 and 8. But these children of 5 is greater than 5. So these two are expanded. There is discarded, pruned. And also similarly 8 and 7 are pruned. So they are pruned. Next, second child of node 4. As I've said, since it is still less than the threshold, the algorithm explores it further. But the children 8 and 7 are both exceeds the threshold, so they are pruned as well. So far, the pruned values are 7 and 8. 7 and 8. Next, the algorithm explores the second child of node 5. Here, if you are expanding, what are all the values? 6. 6 is greater than 5. So, these are pruned. So, it is put up in the visited node. Exceeds the threshold, they are pruned. At the end of this iteration, the final pruned values are 7, 8, 6. These values are discarded, will not be explored further. So, coming into this is the algorithm. So coming into the next iteration, these are all the values are pruned values, 7, 8, 6. Which one we have to select it for the next iteration? 6 we have to select it. So in this iteration, the updated threshold is, in this iteration 4, the updated threshold is 4. So here 2 is less than 6, all can be expanded. If you are expanding this 5 and 4, this will be selected. But if you are considering this 7 is greater than 6, 8 is greater than 6. So these two are discarded. And if you are coming into this 4, 8 is greater than 6, 7 is greater than 6. So these two are discarded. And coming into this 6 is equal to 6, 6 is equal to 6. So this may be, this will be expanded. And coming into these two lines, 6 is equal to 6. So this can be further expanded, 13 and 7. But here we have to stop. We have to prune this case. And here 7 is greater than 6 and 9 is greater than 6. So these two can be discarded in this case. So they are pruned. The second child, so okay, similarly it proceeds. So finally, the pruned values are, if you are considering all those here up to this, here this green color values, the pruned values are 7, 8, 9 and 13. Among these three, so all these four values, the final pruned values are 13, 7, 8, 9. Which one is having the less value? The 7. So we have to select by end of this iteration. So what I have said, the final pruned values are 13, 7, 8 and 9. These nodes are discarded and the algorithm will proceed to the next iteration with an updated threshold. What is the updated threshold? 7. So here we are writing in the iteration 5, the updated threshold is 7. So we have to start from here. 2 is less than 7. And similarly, 4 is 4 and 5 are less than 7. So these are all expanded. 7 is equal to 7. 8 is that is 8 is greater than 7. This will be discarded. So in this iteration, the updated threshold what 7. What will happen over here? The child for these two are expanded will not have any problem. 7 is equal to 7. The algorithm explores its children. So it has been exploring, but these 12 and 14 are greater than 7. These will be proved. So they are proved. The second child of 5 is what 8. 8 is greater than 7. So it is pruned as well. At this point, the pruned values are 12, 14, and 7, right? Okay. So in this case, next the algorithm explores 8, no 8, not 7. So next the algorithm explores the second child of 4, 8 and 7. 8 is greater. This will be pruned. This we are going to keep it 13 and 8. So these two will be discarded. So this will be put it in the visiting node. So finally, the algorithm proceed to explore the second child of the root node and here root node and here 6. 6 is less than 7. 6 is less than 7. So we are exploring over here. 8 here we are stopping. This will be explored, so 8 and 14, and this will not be explored because greater than the 7. So algorithm stops, and the threshold value, that is 8 7, and the visitor values are 8 9 12 13 14. So next iteration 6, so in this case iteration, so from this one we are taking it as so far the pruned values, and here the finally the pruned values are 12 14 8 13 and 9 in this step. So just see this slide, and whatever I have explained here I have given in terms of written. And this you can see, among this one we have to select it for the threshold for the next iteration. So in this case, in this iteration, so here 12 14, which one we have to select? We are not sorry, we are not selecting 9. Which one will be selecting? We'll be selecting 8 as the threshold. So in this iteration, the threshold is updated to 8. So here this is the last iteration. So based on the least pruned value from the previous iteration, the current node is set to 2. So from here all will come. All values are less than 8. No, and here it up to this will go. But here we are pruning. Here we are pruning, and this been pruned. This is alone. This is also pruned, and 7 it will go. This is also pruned. This will not be pruned. This will not be pruned. This will be considering. And finally what will happen is and here 6 and 6 6 it is less than 6 is less than 8, and 8 equal to 8. This will be pruned, and that is this will be expanded explored, and this will be pruned, and this will keep, but there is no children for this. And if you are expanding this 15 and 16, we are finally getting what? We are getting the values 15 and 16. The second child of 8 is 15, and what is the second child of 15 and 8 we are getting. So we are not exploring over here because we are nearly the it is equal to the threshold. So 15 and 16 are examined. Finally 15 and 16 are examined at and 15 is the goal node. So here 15 is the goal node we are reaching. So the iteration is stopped and the goal path is found. What is the goal path now? 2, 5, 6, 8 and 15. So I can write it as 2 2, 5 2, 6 2, 8 2, 15. Very easy algorithm to understand. Hope everyone understands. So this is the last slide content, the last iteration content. So here the pruned values are 12, 14, 16, 15 and 13. And the final value, the goal path, the exploring the second child. And what is the final value? 2569. So this also you can keep, and here you write it. So coming into the application, so this so the goal path is found. The roots are 2 to 5 to 6 to 8 to 15, which I have shown to you. And coming into the application, the IDEA algorithm efficiently combines the strength of the depth first search and heuristic function, providing a balance between memory efficiency and optimal path finding. And so no, this by pruning, and also this is being used in the 15 puzzle algorithm and also NQ problems. The algorithm efficiently handles the exploration of possible configurations, pruning unpromising paths, and ensuring memory constraints are met. If the memory efficiency nature makes it an excellent choice for problems with large search spaces, specifically, and memory usage is a critical factor. By combining depth first search with the heuristic evaluation, IDA Star strikes a balance between finding the optimal solution and managing memory effectively, making it a robust solution for memory constrained problems. And coming into the conclusion, the ideas are effectively combined. This is the memory efficiency and optimal path finding. And here IDEA algorithm combines the strength of depth first and heuristic functions, offering balance between the memory efficiency and optimality. By pruning the unpromising paths during the search process, IDA Star is capable of managing larger state spaces compared to traditional algorithm, making it highly suitable for complex problems. While it may not be the fastest option, IDA Star guarantees finding the optimal solution while utilizing significantly less memory, making it an ideal choice for problems where memory constraints are priority. Its ability to explore and prune based on heuristic evaluation ensures efficient search performance with minimum memory usage. So these are all the conclusions of this IDA search algorithm. And IDA star, as I've said, IDA star is a memory efficient algorithm because it combines the principle of what I've said, DFS, depth first search, with the heuristic based pruning. And unlike A star, which stores all expanded nodes in memory, IDA stars only keeps track of current node search path, significantly reducing memory space. The algorithm uses a threshold based approach, incrementally increasing the threshold value based on F score. This is very, very important. Based on the F score, sum of the actual cost. By pruning unpromising path at each iteration, IDA store avoids storing nodes that lead to dead ends, making it memory efficient even when dealing with the large state spaces. However, it is largely that is, it is lengthy process because it requires repeated searches with progressively increasing thresholds until the goal is found. Despite this, IDA ensures optimal solutions by systematically exploring all possible paths within the memory constraints. Although the algorithm's time complexity may be higher due to the repeated searches, its memory efficiency make it suitable for solving the problems with limited memory resources. Hope all you understood about this IDA search algorithm with an example. The remaining things we'll discuss in the next lecture. Thank you.